Hello everyone, I hope you are doing good. Since we released our online reverse engineering training, we've received a lot of feedback, and one of the things that kept coming up is that we didn't cover Go malware in the course. A few weeks ago, I had the opportunity to work on one such sample, and so I felt it would be great if I could share it with you. So today we'll be looking at a malware sample that is written in Go language, and while I don't usually look at the syntax and or specifics of the various languages that I have to work on, as much as I'm loath to admit, Go is so different from the other languages that we won't really be able to escape this. So the first thing that we'll be doing today is look at simple Go programs and study the generated code. It's no surprise to me that there is so much demand for a Go tutorial. More and more security tools are written in this language, and for instance, some of the red teaming tools used by FireEye and which were revealed in the context of the very incident that we'll be looking at were developed in Go. The threat actor also chose this language to develop their own tools, and you see, usually compiled programs always end up looking something like C. C++ is C with extra function pointers. Delphi has this weird calling convention, but at the end of the day, it's still pushing and popping things on the stack like it's 1985. With Go, all your expectations go out the window. The compiler is generating code that looks nothing you've seen, and so we will really have to start from scratch and get acquainted with this whole new paradigm. I think Go is becoming so popular among malware authors just because analysis tools also have a hard time applying their old heuristics to them. As for the malware that we will be analyzing, it is called Sunshuttle. It was disclosed by CISA in March 2021, and it's a fully featured backdoor that was discovered in the context of the SolarWinds incident. I'm pretty sure that you've heard of it because it was one of the most significant cyber attacks in recent history. Long story short, a software company providing IT management software was breached and leveraged to infect very high-profile targets. So if you'd like to know more, we have a couple of blog posts about it on SecureList, but obviously other vendors have also published extensive research about the threat actor. But anyway, let's talk a little bit about Go. The first thing to know is that it generates statically built executables. The whole Go runtime and necessary library functions ship with every program that you compile. And as we'll see, a simple hello world program weighs around 2 megabytes. This is, in essence, the reverse engineer's nightmare, as binaries are filled with library code. Things used to be a lot worse, though, because since version 7.6 of IDA Pro, there was a lot of improvements introduced when it comes to Go binaries. It looks like it's quite efficient at recognizing standard functions now, which makes our lives 100 times more enjoyable. And not that long ago, you had to use third-party plugins to maybe get this information. When it comes to writing code, Go feels a lot like a scripting language. No semicolons, the syntax feels very uncluttered. It has strong typing though, and the compiler is very strict about a lot of things. Have an unused variable somewhere, the code won't compile. Have an import that isn't needed, the code won't compile either. You can think of Go as fascist Python. It's like the designers had been watching people shooting themselves in the foot with C for 30 years, and they went like, this stops now. There is no exception mechanism in Go, but functions can have multiple return values, which is important. A very common pattern is for functions to send back the result and then an error object, which hopefully will be null or nil in Go. The silver lining is that the standard library provided by Go is extensive enough that most operations, like opening files, establishing connections, encrypting stuff, will rely on it sooner or later. The way that we will approach Go programs is to try to rewrite the original scripts by tracking the library calls and their corresponding arguments. When we encounter a function that we don't know, we will be able to look it up in the official documentation, which contains everything we need. Another point of interest is that strings and constants used in the program get mashed together and put together in the binary. I've seen this for integers too, which can be a bit surprising, but you'll see what I'm talking about. So without further ado, let's have a look at our first Go code and the compiled binary to see if we can make sense of things. So here we have our first Go program. The entry point is the main function that is located in the main package. In it, I have defined another function called sum, which I like to do because it always showcases how the calling convention works. And this sum function takes 3 arguments, a, b, and c, which are integers, and it returns an integer, which is a plus b plus c. Here in this main function, we call sum with arguments 1, 10, and 100, and just print the results. One thing I'd like to point out is that this code was compiled with disabled optimizations, because if you don't, then the compiler is smart enough to inline everything. So as promised, you'll see that here the generated binary is about 2 megabytes big. Let's just run the program to show that it returns the correct value as advertised, like this. Okay. And now let's see how it looks in IDA Pro. So here I already navigated to the entry point, but if you look at the functions window on the left, you will see that IDA Pro did a good job at recognizing all the library functions there. So you see a runtime, go panic, runtime, etc., etc. So all the functions are named correctly, which is going to help us a lot. Now, the main function is going to be, usually the functions defined by the user will be package name underscore and then the name of the function. So in our case, main underscore main, which you can look up here. But you'll also notice that the functions that we created are located at the very bottom of the function screen, at the very end of the binary. So let's just follow this main function here. And the first thing that you might notice is that the usual push EBP, move EBP, ESP is nowhere to be seen. Instead, you have this move RCX GS28 and then a comparison here to make sure that the stack is big enough. And if it's not, then you have this call to runtime more stack no CTX T. But usually this code there is present at the beginning of every function, and you can completely ignore it because it was inserted by the compiler and has no bearing on the analysis. Moving on, you have this main underscore sum function, which is ours. And if you look at how the arguments are passed, you'll see that you have our 1 here that is moved directly on the top of the stack. And then you have this argument here, which is 10 and 100 that come immediately after. And this is the way that Go passes arguments. Arguments are not pushed or passed through registers. They are directly copied onto the stack at the correct position. And inside this function here, there is no prologue and no epilogue as well. And so the compiler knows exactly where on the stack those arguments are going to be. And so those are going to be accessed directly. Okay, so here, as expected, you have arg0, 8, and 10, which are all added together. And then the return value, the result, is also pushed back directly on the stack. Now, if you try to follow those, be careful because, of course, when there is this call here instruction, call is going to add the return address on the stack. And so here, let me press Q like this to delete the variables. Here, RSP plus 8 is not going to be the same RSP plus 8 as in this function here, because simply there is one more value on the stack. So everything is, there is an offset of 8 every time. Now, normally, IDA Pro is going to, by default, create variables for you. And this is something that is very helpful most of the time. But the problem with Go is that the compiler, being quite smart, when the position on the stack is not used anymore, then the compiler has no qualms with reusing it in the future. And so, as you'll see here, you have this var 80 here that first is used to store our argument. Then later on, we have another use, which I'm not exactly sure of what it is. And then again, at the very end, you have a value 2, which is stored there as well for another function call. And this is going to be something very important when it comes to reversing Go binaries. It's the fact that renaming variables really won't help you at all because those variables are going to be used for very different things throughout the lifetime of the function. And so trying to, give names to argument is going to be a fool's errand, and you, I think, should not try to do this at all. So instead, you can press Q on those to just have references to the direct offsets on the stack, which I think is not exactly a lot more readable, but at least it's not going to confuse you with those vars that don't mean anything. And yeah, here in the after the function call, you have this RAX, which receives the return value, but it receives it again from the stack and not from the sum function. Okay, then moving on a little bit here, you do have those runtime GC write variables all over the place that I'm not exactly sure what they are doing, but you can skip over these. And at the very end, you have this format.println, which was our printing the result here. Okay, so this was a short introduction just to see our first Go program, but now let's look at a more complex one. Our next program is almost the same. The only difference is that our sum function now returns 3 values instead of just 1. So we now have a string in addition, which is the constant rima2, and then an error. And now the main function gets all those return values, checks if the error is nil, and if it is, it still prints the results and also the string that was received from the sum function. So on paper, it doesn't look too different, but you'll see in IDAPRO that the code is already substantially more complex. So let's go back to our main function here. The invocation of the sum function looks exactly the same, but if you go inside of it, you'll see it's a bit more complex here. So you still have those, move RCX GS28, which we don't care about. So let's black it out. And we have the creation of this error with errors.new, just like in the code here. Also a reference to our rima2 string and our sum, which probably is happening somewhere, maybe here and here. So trying to track down which value goes where in the stack is already proving to be a bit difficult. If you come back after the function call there, then you will see that all those return values get copied from the stack to registers. So here in RAX, RCX, etc. And well, here trying to figure out exactly what is on the stack at which location, I think is going to prove extremely difficult, especially considering that immediately after this function call, we see the exact thing that we hate to see when reverse engineering a program, which is values being moved around for no apparent reason. One of the reverse engineering teachers that I had was always telling me, no guessing, Ivan, look at the code. And well, I pray he never sees this video, because today we're going to be doing the exact opposite of this, which means we will not be looking at the code and we'll be doing a lot of guessing. And my approach when trying to understand what a Go binary does is to completely give up on all those stack manipulations, because trying to track them down, I think, is way too much effort, and just try to locate all the relevant API calls. Okay, so like this one, main sum, which is a user-defined one, but others like this, well, later down here, runtime conv string, I think we can guess that this is some kind of API conversion from the Go library going on, and at the end fmt_println. So what we're going to do is we would put a breakpoint there on fmt println, and we would just look at the arguments and look at the return values. And this, I think, is the quickest way that you're ever going to figure out what is going on inside the Go program. One of the good things that we have working for us is that even though following things around on the stack is very difficult, trying to see the arguments of a function is in fact quite easy. If you look at this sum function call there, you'll see that the arguments are moved immediately before the call, and the return values are copied back into registers just after. So with your debugger, it's going to be extremely quick for you to see exactly what goes in and what goes out. And from here, try to reconstruct the semantics of the program. So I think this is all the theory that we need for now, and we're going to move on to Sunshuttle. I'll see you in a second. All right, let's get started with Sunshuttle. One of the first things I'd like to mention is that initially this sample was packed with UPX, although unpacking it was really a simple matter of running UPX-D and then the name of the program. So I'm just going to skip over this step because I did it already. And also, I already removed ASLR from the binary because we're going to follow it inside a debugger, so it's going to make things easier for us. So this is what the program looks like in IDAPRO. You see that a lot of functions are recognized properly, which is really cool. And we're just going to go to this main function here. Okay, and one of the first things that you might want to try is to look at the decompiler output, provided that you have access to the x64 decompiler, of course. And one of the things that you will notice is that, well, it's not exactly a lot more easy to read than the disassembly. You have a lot of variables, a number of which appear to be undefined or used before being ever assigned a value. And a number of objects like this being defined on the stack in a way that doesn't immediately make sense. And you'll see that this is a pattern that comes out a lot. So if you follow this function, for instance, we'll see that you also have a number of variables here that I believe are coming from the stack, from the caller function, but that IDAPRO is not really able to track properly. One of the things that I've noticed as well, looking at the pseudocode window, is that even though IDAPRO, I think, is doing a pretty good job at decompiling code in a generally speaking, well, for Go code in particular, sometimes I found that it misses entire lines of function calls, which can be problematic. So it's really a good idea to keep an eye on the disassembly window first and foremost. So anyway, let's start with this main function. Here we have the usual stack setup that we're going to skip over. And there, our first function call, which is net underscore interfaces, which would translate to the interface method inside the net package. So let's look at what it does. So I'm going to go to the official documentation, look at the net package, and then the function in there called interfaces. And there it is. And you'll see that this function returns a list of course, the systems network interfaces. This list is going to be provided through, I think, this argument there, and we have also an error value that is returned. So let's try to write pseudocode that corresponds to this function. I cannot promise that this pseudocode is going to be accurate Go when it comes to the syntax, but it's going to give us a general idea of what the program is doing. So interfaces and error equals net.interfaces. Like this. Okay, and then if we go back to the Go code, we see that as expected, we have two return values that are copied back into registers. And we have a test here that checks whether a value is equal to 0, which I'm not going to be able to track all these Go arguments because of the way that they are handled inside the stack. But what I can infer from looking at this is probably we're going to do a check on this error there. So here, probably this is a check to see if the error is 0. And if it's not, then we go into this block and call OS exit. Otherwise, then we move on. So let's try to update our code here. So if error is a nil, then we have os.exit with a value, an argument there, which is 0. All right, and otherwise we move on. Next there, we enter this big loop. We see it comes back all the way up there. And this code here is exactly what I don't want to be, looking at line by line, because you see all those values being moved onto the stack in a way that I think is not immediately obvious, at least not to me. So let's try to look at the function calls instead, maybe use a debugger and see if things make sense. So first, we do see that there we do have a call to this hardware ADDR function. So let's go back to the documentation. Okay, there it is. And we see that it returns a physical hardware address, so a MAC address, as an array of bytes like this. And then we have a call to the string function. So based on the structure of the code, we can assume that we have something like this. So if or for something interfaces, and then we have this, I guess maybe something like this, I in interfaces, and then I dot hardware ADDR like this, maybe, yeah, dot string. I don't know if it's a function. No, it's a type. So maybe just like this. And then what do we do with it? So if you see something like this. Like, you know that the return value here is probably going to be a string, and then you have a reference to a value, and then in the stack an offset, and the offset plus 8. And strings are defined like this in Go. So you have a structure that is first the offset of a pointer to the characters in memory, and also the size of the string here. So here, very likely in RAX, we're going to have the size of the string, and here in RCX, we'll have the actual bytes. We have a test here on RAX, and we check whether the size is indeed 17 characters, like this. And then we have this comparison here, runtime mem equal, which I think is a fairly obvious reference to a string equals function. And it looks like this string is being compared to this value there. One thing you'll notice about Go variables, Go strings specifically, is that they tend to be packed all together in memory, and it's a bit inconvenient for us because we would really like them to be separated by null bytes, or, you know, I don't know, at least line feeds, carriage returns, and so on. And the way that the compiler works is just, you know, garbles them all together side by side. So here our MAC address would end up there, and the way that they are referenced is usually you have the pointer here to the character somewhere in memory, and then a size somewhere else. Let me see if I can find the size here somewhere. Don't see it immediately. Probably RCX. Yeah, RCX or RAX. Yeah, RAX here is still 17, so it's reused because we expect this one to be 17 bytes as well. Yeah. Okay. So let's update our code. Just copy this properly. Like this, and then something happens, I guess. Yeah, and if this is the case, then again you have this os.exit function call. So if you want to know more about this MAC address, I guess we can always look it up. Well, let's try putting it on Google. And here you will see, okay, references to, of course, this malware specifically, but you'll see, for instance, links like this one that mention that this MAC address value is actually the Microsoft Hyper-V network adapter. So this is a MAC address for a virtual machine, and in essence, this test is here to ensure that the program is not running inside a VM. Okay, and then we move on back there and loop on all interfaces. Now, of course, here I know I'm making a number of guesses, but if you want to make sure that everything there is correct, and all you have to do is open the program in the debugger, put a breakpoint there, and follow through all the different steps. And I promise that everything is going to appear as clear as day. Okay, so when the loop is over, we do end up there. So we have this time.now function here. So this function call, I'm not going to look it up because I think it's pretty obvious what it does. I'm going to skip over those two blocks because I'm not exactly sure what they do, and I don't think they are really necessary to understand what is going on. But okay, so if we move on, here we have, I think I'm missing something. Oh yeah, sorry, I was a bit I went down a bit too far. So this is our time.now function call. Here we have this operation, which I'm not exactly sure what it does. Probably, I guess we could look up this number too. Okay, so it's not exactly clear yet to me, but it really looks like this is related to dates. So let's skip over this calculus. and you see that you have this rand seed function. So I think it's quite obvious that we have something like rand seed like this, which is the usual call to initialize the randomness generator of a program. And then we have this call to main define internal settings, which looks like, since it's from the main package, more developer code. So it's something that we are more interested in. So let's now get into this function. In this function, skipping over the setup stuff, we start by referencing those two global variables there. And you'll see that they are just one after the other. And the first one is the bytes of the string or pointer to them, and then the size. So we're going to just create a quick structure here to represent ghost strings. It's not something that we necessarily have to do here, but who knows, it might be useful in the future. 1, 2, 3, 4. Let's name this data, and the other one is going to be size. And this type is going to be a car pointer, like that. And then if you go back here, we can press Alt Q to change the type to a string. Okay, so let's move back there. Oh, maybe we can rename it as well. str config that. And this string appears to be moved around on the stack, and we have this tmp and then the number 4 being moved on the stack as well. And we have this function concat string, which I think is it's fairly obvious that it is a string concatenation. So let's open a new function, which is called define internal settings. Like this. And by the way, this one should be a function called main. Like this. So the first thing we do is probably something like s equals something like this. Okay, and then we have a call to ioutil read file. So let's go to the documentation here. And as the name implies, this function reads a file and returns all its contents. And you have here it takes as input a string, which is going to be the file name, and then the bytes will be, well, the bytes of the file and then an error. So let's try something like this. Remove this variable creation there. And again, let's take contents and also error equals something like this. All right, and then we have a test. So depending on whether this value on the stack is 0 or not, then we go either in this branch or the other one. So I think it's also a bit obvious here that depending on whether or not the file exists, we're going to follow one branch or the other. And since we don't have the file on our system, then we're going to first look at this branch here where the file doesn't exist. So let's follow this red branch, and we end up there. So we have this open file here with this argument here on the stack. So let's change this to octal representation. So 666 is going to be the file permissions, and earlier, probably in RCX, then we still have our I don't know, probably, yeah, RCX is here. I guess it might still be the file name, but I'm not exactly sure. But one way or another, this file name there is going to still end up down there, and it's going to be the same file that we this time create. I mean, we could check that in a debugger as well. Okay, so let's look at the arguments of this open file. might be in another package, OS open file. Okay, there it is. So actually, we kind of need the variable in the end. Like this. And the second argument is going to be a flag, which I guess represents oRead-only or oCreate. All right, let's not look those up. And then the permissions. Probably oCreate here, and then 0666, like this. And the return values are file and error. I don't know if I can reuse the error variable there, but I'm going to do it anyway. Doesn't matter if the code isn't exactly correct. And then move on. So we have time.now and then time string. One thing you might notice here is it might seem like this second function there, time string, has no arguments, but in fact, I think that the way that Go creates its stack makes it so that the return values of this one can be immediately reused in the next function. So it really is something like time.now dot string like this, or maybe time.string of this. All right, and then we have this function called getMD5hash, which comes from the main package, so it's user-defined code, probably, but based on the name, I think we can have a pretty good idea of what it's doing. Let's update our code like this, and then for completeness' sake, we are still going to go into it and quickly verify that everything is what we expect to be. So new object creation, we don't know what it is based on probably some type information that's in there. I don't know how it works, but it doesn't really matter. I can skip over this. What it does, we have string to slice byte, which is a conversion between a string and then to obtain its well, the corresponding character bytes. Crypto.md5 digest write, so we write the bytes that we read into an MD5 hash object, obtain the sum, make slice obtains some sort of it's a way to take the subdivision of an array. So here I'm not going to look at the argument, but maybe we only take the first 32 bytes or something like this from the checksum. Then we have hex encode and then bytes to string. So in essence, what happens there is we take something as an argument, I expect, and then we convert it to bytes. We compute the MD5 hash of those bytes, convert them to, or encode them as hex and return the value as a string. So yeah, no need to get into more detail, I think. So let's call it S. Like that, and we're going to just make sure that we got everything correct there by quickly using a debugger and verifying that this returns the MD5 hash that we are expecting. So what I'm going to do is now run this program into hex64dbg. One thing I'd like to point out though, before we open this program inside the debugger, it's that x64dbg will not be able to recognize all those function names the way that IDA does, because this is accomplished through some X-rays dark magic, I guess. So when we're going to execute code like this, for instance, we won't see call os_open file, but just some address in memory that won't be very helpful to us. So it would be pretty cool, right, if we could just export all those function names and have them in our debugger. And this is actually something that's quite easy to do. There are several ways you can accomplish this. One of them is using a plugin called x64dbg IDA. And you just select it here, click export x64dbg database, select a name for it. and then press save. And it's going to take a few seconds, but then it will allow us to export everything and import it into x64dbg. There's another plugin that does this, which is called Label List, that I haven't tried myself, but I hear very good feedback about it, so feel free to give it a try. All right, so after 30 seconds or so, my database has been exported. You can see here it's about 88 megabytes big. And if you open it in Notepad++, you'll see that there's something that you need to be careful about. And it's the fact that here the module name, which is sunshuttle.exe for me, should be exactly the same as the file that you're going to load it in a debugger, including the extension here. Because if you don't, the database will still be imported correctly, but the debugger won't be able to associate those names that you imported with the current program, so it won't do anything. So let me just load Sunshuttle inside x64dbg here. All right, and now I'm just going to go to File, Import Database, and I'll just browse to my folder in order to choose it. Start Sunshuttle, and there it is. So you just press Open. And then let's just go until the entry point here. And there it is. You can see that the names have been correctly imported there. You have sunshuttle.runtime set TLS, for instance, etc., etc. And this is going to make our lives easier. So let me just go back here. And we're going to make sure that this MD5 hash corresponds to what we think it is. And to do so, we'll just set a breakpoint here on time.now, for instance. Copy the address, and then set a breakpoint there in the debugger. So let me do this like that. F9 to run, and here we are. So I just skip over the two functions, and here you see that we have the current date, which has appeared in the debugger. So let's just follow and dump the current value, and we're going to copy this whole value with Control E, and then select everything. And we'll calculate the MD5 hash of this string, just to make sure that it corresponds to what is going to be returned by this get MD5 hash value. So let me just skip over. Oh, yeah, this is one thing that happens when you're debugging a program written in Go. Sometimes you see here, I just pressed F8 to skip over an instruction, and I just ended up somewhere in the code that was completely unrelated to what I was doing. And for some reason, Go programs sometimes, for some maybe synchronization reasons or thread reasons, get switched to somewhere else. And the way I figured to reach back where you were is just to go to debug and then return, or just execute till return, press F8. And here you see I'm just back to the exact instruction I was before. Anyway, so let's just go until this get MD5 hash function. And here I'll go to CyberChef. And I'm just going to calculate in advance the result that I am expecting. So like this, put the input string there, look for MD5 here. And we are looking for a string that starts with 2B and ends with 4E. And now just press F8 like this. And yeah, 2B at the beginning, 4E at the end. So this is exactly what we thought was going to happen. So good. All right, so now let's see what happens. Now the value that comes from the stack here, which is probably the return value, gets copied into this variable there. So let's just make sure that this is our MD5 hash. Let's just skip over here. And RAX contains 20, which very likely is the size of our string. So let's update this in IDA Pro. And then if this value, which is, I don't know what it is, let me check. This value appears to be 0 for us. Oh yeah, okay, now I remember. So you see here you have this runtime underscore JC write barrier, and those calls to JC write barrier get inserted almost everywhere. So let's press X and you'll see you have like infinite number of calls or references to this function. And this is not developer code. This is something that the compiler inserts to, I don't know, probably garbage collect all the unused variables. And this variable, global variable there, is also used all over the place. So let's just rename this GC related and forget that it ever existed. Yeah, and we can ignore it safely whenever we see it again. So let's move on a little bit here. And see, this hash was in RCX, and then it was copied into this global variable. Here. So let's rename this time now hash. Perfect. All right, now moving on. Now you see here we have another character string that is being used. It looks like a user agent, so let's follow this. Yeah, and again, this looks like a character string, so let's convert it. Yes, and as you see, you have the bytes, and then its size. So let's rename this variable like that. So what happens to it? It looks like the string is converted to bytes. Then we have this global variable that we don't exactly know about, and then this encode to string. Now, looking at this, you see this base 64, and you might think, okay, I know what this is, so there's no need to look up documentation. But actually, for this time, I think we actually have to. So let's go back to the Go documentation. I think it was something like this. Okay, and then look for base 64. All right. And we're looking for a function that is called encode to string. And there it is. And looking at this prototype, then you might be surprised because we know what this is. This is the type of the input, and this is the type of the output of the function. But then what does this mean, right? And this enc pointer is what is called in Go, I think, a receiver. And it's a sort of object that is going to apply the function. If you look at the example there, you see that encode to string isn't directly a function that is called from the base64 package, but a function that is called from something that looks like a class, which is std encoding there. So you have base64.std_encoding.encode to string. And the way that this is implemented in ASM is this receiver argument, this std encoding, would be pushed on the stack as well on RBX and then moved there. So let's look at where this function, where this argument comes from. And you see that it's created in a function called base64 init. And there you'll see that it's associated with the standard base64 alphabet. So looking at it, A to Z, etc., the numbers, and then plus and slash. But if you go down a bit further, you'll see that there is actually another encoding that is available, which is almost the same, but at the end, it's finished with a dash and then an underscore. So we really need to be careful there because depending on which of those variables or which of those encodings the base64 is going to be applied to, then of course the result is going to be slightly different. So let's rename this base64 std encoding. And this one that ends with an underscore is actually called URL encoding. Now, normally you could ignore this subtlety and you would never, well, see the difference inside the code because most programs are going to just use the std encoding. But it turns out that in this specific malware, both encodings are actually used. So this is a pitfall that might get you scratching your head somewhere down the line. Anyway, so base64 encoding applied to this user agent that we had here, and then a reference to a global variable here. Let's move on a little bit with the with our debugger. So let's move on there. Okay, and then base64, let me just skip over. And yeah, we see that we have this TW, etc. Let's just follow this in the dump as well, copy it. And again, use CyberChef to make sure that everything is still happening as expected. So we copy this here. Base64 decode. Oh, actually, I can click on this magic wand there. Oh, and you also have user agent parsing there. So yeah, everything happening as expected. And then we move on and we see that at the moment, this user agent doesn't appear to be used. Next, in RDX, we put a global variable that appears to be 5, right? Yeah. So as I mentioned, sometimes those global variables are stored like this. So those constants get stored as global variables, which I think is surprising, but maybe it's related to the way that this program was developed. At the moment, we don't really know what it is. We know that this number 5 is going to be converted into a string there, but we don't really know what it represents at the moment. Let's just rename this to global 5, and at least this will let us know later on when we encounter it again, if we do, that we've met it in the past, and so we know where it's coming from. And then the next one is mostly, it looks the same. It's like number 15, and we also have this format in. So let's rename this global 15 as well. And now something which looks again the same, except this time we don't know what the initial value is. So let's just go back into the debugger and see what's in this place in memory. So let's just press Ctrl G, Ctrl V. Okay, put a breakpoint, F9. And there you see that at the moment here, this variable is 0. So for now, again, let's rename this global 0, and maybe later on things are going to make more sense. Again, all those numbers that come from, we don't know exactly where, appear to be converted to strings. And later down the line here, you will see that there is this big concat string function that is happening. In the middle, everything we hate, like memory being moved around for no apparent reason. So we're not going to be tracking down all of those. I'm just going to make sure that we note those variables that we encounter just as a way to remember them. This one I think is also going to be 0. Let's skip this. Here, and yeah, it's also 0, so let's name it global 0, 2. And now we are just going to skip over all this because we don't want to get lost in there, and put a breakpoint at concat string and just look at the return value. Let's copy this, go into the debugger. I'm going to remove my previous breakpoint. Doesn't look like I'm in the right place. Probably I copied the incorrect address. Yeah, let me see again. Okay, Ctrl G, Ctrl V. Yeah, much better. And I'm going to press F9, reach my breakpoint, and then F8. And somewhere it looks like I got my return value. Like, it looks like it's in RBX or RSP plus 20. Let's follow this in dump. And I'm going to copy everything again and look at it in a better environment, like my notepad. All right. And so here we see some of the values that we've seen before separated with this pipe sign. So first, our MD5 hash of the current date, then those numbers 15, and then 15, 5 and 15, and then zeros, and then our user agent encoded as base64, and that's it. So we don't know what those values are for now, but, well, at least it looks like this is what's going to end up inside the configuration And at the end of the day, then maybe later down the line, we'll be able to know more about what they represent. Here, now we have obtained this configuration or generated it with default values. And looking a bit later in the code, you see that it's going to be written inside the file that was created after being converted to a string and 2 bytes for some reason. In the middle, we have some encryption function that is happening. And I'm not going to go too deep into this function. One of the things that I want to make sure is that we kind of know, generally speaking, what is happening, but I don't really want to go too deep into the details. So it looks like this input is going to be encrypted with AES. We have this new cipher function. And then going down, bytes repeat, which I imagine would be some kind of key expansion. Grow slice makes an array bigger to make sure that data can fit inside of it, etc. Let's skip over this. And then new CFB and base 64 conversion, this time with the other encoding, right? And that's it. So it looks like our inputs, our configuration will be encrypted with AES, and then it will be converted into base 64 with the URL encoding. One thing I'd like to know though is where this key is coming from. It doesn't look like it's from this function there. So I'm going to go back a bit and look at what is passed to it. So let's just put a breakpoint here. Okay, there it is. It wasn't too far. All right, so those values here, this 560 MHN, etc., looks like it could be probably a key. Let's move on a little bit here. Yeah, so this here looks like this will be the key, and this is the value to encrypt. What is the size of this key, though? Maybe somewhere in REX, and there would be the size of the string. I don't know. I think REX might have changed in between. Yes, it was here. Let's look at RSP plus 8, follow and dump. And this size was 20, which looks like a pretty reasonable value for an AES key. So let's copy this. Let's go in the dump, value RSP, and then copy those 20 bytes, Control E, like this. And we're going to use CyberChef again. So let's delete this. We'll have some base 64 in the configuration file at the end. This alphabet is not the correct one. We are using the URL encoding here. And then after that, we have AES, decrypt, and we know that the key will be this. It's not hex, it's, I don't know, Latin one, I guess. The mode was, if I recall correctly, CFB, right? CFB, correct. And the input will be raw. All right, I don't know about the IV, I haven't seen it. Maybe it's one of those random calls that came earlier, but I'm not sure. Okay, let's go back to the debugger, skip over the function call. And there we appear to have our return value, follow and dump. Okay, let's copy all this, use this here as the input. Okay, and the IV appears to be incorrect. Oh well. I guess we could look at this function in more detail to see exactly which one of those contains the IV. Let's try with the null one, with zeros. Yeah, perfect. If you look at it, you see that here we do have our values that appear again. So there is a little bit of garbage at the beginning, but no matter what the reason for this is, I mean, at least it looks like we're pretty close to what we expected. So there might be one thing or two I'm missing, but generally speaking, I think all my predictions so far, all my guesses weren't that far off. All right. So we have this encryption function that now we understand a little bit better. And then this main write file creates, so we store our configuration inside this config.dat.tmp. And at the end, close the file and return. So that's one function down. We know how the default configuration is being created. Just for completeness' sake, we're going to look at the other branch where the file already exists. And I expect that, I'm going to skip over things, but I expect that it's going to be very similar to what we just saw. So here, the decryption function. So we read the bytes that we got from the file. We decrypt them using, I guess, AES. And then this base64 with URL encoding. And then for all of these values, we split them based on a character, and this character will be the pipe sign you see here. Let's rename this like that. So we split our configuration, and for each of those values, we store it into the corresponding global variable. So first, the time hash, which might be used as an identifier for the backdoor. And then for all the integers, they get converted back from string to integer and stored into the corresponding variables there. So same for the user agent here, etc. Okay, so we don't really know what those values mean at the moment, but at least we know where they come from, how they are stored, and now we can read more of the code to be able to understand what the actual significance behind them is. Let's go back here into the main function and resume our analysis. Next, we have yet another call to time.now. And what follows is what we identified previously as some sort of a timestamp or date conversion. So we're going to skip over this and focus on this block instead, which I think is more interesting. So you see that in RCX, we have whatever the result is of this time.now conversion into something, and it gets compared with whatever is stored in this global variable that came from the configuration. And depending on the result, if the current date is bigger than whatever is in RCX, then we end up in this block here where we call os.exit. Otherwise, this block is ignored and the program moves on. So this means that here in this global underscore 0 underscore 2, we have a date, and also this date has meaning, right? We can probably rename it as something like expiration date, because it looks like it's a date after which the program will not accept to run. So it's probably something that the attacker set up to make sure that well, the program wouldn't keep running forever on the victim system, for instance, if their operation was limited in time or something like this. Now, moving on, we get another use of one of the configuration variables. And again, depending on it, it can be either one or anything else. We can enter this block here or entirely skip it. And in this one, what happens is we have a call to runtime.newproc. And runtime.newproc is a way in Go to create a new thread that executes a function. So let's look at the arguments here. We have RAX and RCX, and RCX here is an offset to a function, and RAX will be the result there of this math.rand.intn, so generation of a random integer. So it looks like this function main false requesting will be called in a new thread, and as argument to this function, probably we are going to pass it the random integer. So we're going to rename this variable into, I don't know, it's going to be a flag, so maybe enable false requesting. Yeah, perfect. And enable false requesting will control whether or not this thread will be created. So let's have a look at this function and see what it does. Okay, so it seems to be a little long, but that's fine. we're just going to skip over things again and try to just figure out what it does by looking at the various functions that it calls. So we have here more random integers generation, and there a reference to a character string, which is cdn.mxpnl.com, which I'm pretty sure is a legitimate domain. And if you look here, you'll see that this random number gets stored in EAX. They make sure it's lower than 14, sorry. And then this integer gets multiplied by 16 here. And then we have this string there, the offset to this domain name gets modified based on this integer that we obtain. So actually, I don't think we're going to see it there, but probably there are other character strings that are moving around, other URLs inside the memory, and one of them gets selected at random. We'll see with the debugger, because I think there's I think we're going to get another one than this cdn.mxpnl.com. Moving on, we have those new object creations, which is something I don't really like to see because it's quite difficult to track what those objects are actually, because they are created based on some type information. I don't really know how that works, but we can just skip over it anyway. So let's move over those. And here we see new HTTP new request with context, which I think is fairly indicative of an HTTP request being created. And then moving on, we have sort of the same construct with integer generation, comparison with this time 4, and then multiplication. And then at the end, another URL, which this time appears to be used as a referer. So this looks like an HTTP request being created based on some hard-coded values. Here you see this canonical MIME header key function. I'm not exactly sure what it does, but it looks like, you know, a way of adding, I don't know, headers to an HTTP request. So moving on, we see the same thing a bit later on. Here, the connection string. Careful, you might think it's connection content ID, but you have to look at the size, which is 10 here. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is just this part. So again, being added as a header. This time the value will be keep alive. Okay, so assignment into a map. Moving on, user agent will be, well, whatever user agent was from the configuration or the default one that we generated before. And finally, at the end, we have this HTTP PTR client.do, which I guess we could look it up in the documentation, but it's fairly obvious that this is the function which at the very end will call this, send this HTTP request. So what we're going to do is, again, check with the debugger that we are doing things correctly. But first, by default, I don't think that this enable false requesting is set to 1. So we're going to use the debugger and change it, of course. So let me go there. Control V. Okay, so this is the place where those values are compared. Okay, and I'm going to just follow this memory address and change this 0 to a 1, just to make sure that we indeed enter our threaded function. And then moving back here, I'll go back into this function there and just put some breakpoint near the actually, let's put it near the URL as a starting point. So I'm going to copy this address again, Control G, Control V, set a breakpoint, press F9, and there we are. So initially the URL is cdn.mxpnl.com, right? And then probably in just a few instructions here, you'll see that the URL gets changed to code.jquery.com. So probably there's the whole list of URLs that the code can pick from. Okay, and then moving on, I'm going to put a breakpoint on this do function. It was a bit further down, I think. User agent is there. And here it is. So let's copy this. Okay, so we reached our do function, and the one thing that we would like to do is to have a look at this HTTP request as it is sent. So what we can do there is we can use a nice program from FireEye, I think, which is called FakeNet. I'm just going to run it as admin, like this. And FakeNet is going to intercept all outgoing HTTP requests. You see there are already a number of those being generated by my system. And it will allow me to look at the exact output. So let's just go back to the debugger, press F8. Okay, and we gone over this. And see here we have this get/HTTP. Host is codejquery.com as expected. We have our user agent, connection keep alive. The referrer was not Twitter as we've seen in the code, but this time was randomly selected as bing.com, accept encoding, etc. Okay, so it looks like, again, we got things mostly right. And then immediately after, you see that the request is going out, but it doesn't appear to be used in any way. So it's not like the program is obtaining any data from the internet there. It's just generating some requests and ignoring the result or the output, because apparently the only point of those requests is to generate some legitimate traffic that won't raise any suspicions. So, for instance, maybe that if a sysadmin sees a program or a machine that generates some traffic that looks like, normal user browsing, then probably I guess it's possible that they won't look into it further. And at the very end, you see that you have this whole jump to the very beginning of the function here, and we get back there, and you see that we have a comparison between RAX, which was 0 here, and RBX, which was the argument. So this random number actually controls the number of fake requests that this program is going to generate. Okay, so now I'm going to move back a little bit. Going back to our main function. Okay, there we are. So here, again, time.now, and then conversion, and then the results get stored into this variable. So I guess we're going to name this time now. Let's see if it's used at another point in time. Only in the main function, so we'll see. And here we have a call to this function called main request session key. So it looks like we are now going to have an actual interaction with the C2 server. So I think this is as good a time as any to take a break here. So let this be the end of part 1, and I'll see you in a bit for part 2.